Hi everyone, welcome to the Central Limit Theorem lab tutorial. We're going to start by opening StatCrunch and clicking on the applets button, and we want to click sampling distributions. Now in the Word document for this tutorial, I have a little snippet of this dialog box here. The first basically half of this dialog box, these top options here, are for you to determine the parameters of the population. So you can decide initially what sort of group that we are selecting the sample from. It could be uniform, it could be skewed. Bell-shaped gives you the options of defining the normal curve with the mean and the standard deviation. And then below that, once you select your sample, what are the statistics that you are creating the sampling distribution with? You can select the mean, the median, the variance, the standard deviation, the min, or the max. So you can pick one or two different statistics to create your sampling distribution with, and then you just hit compute. So just to show you what all the different plots look like, I'm going to leave it as uniform and the mean as the statistic that we're collecting, and I'm just going to hit compute. So the very top plot here, which basically looks like a gray box, that's the population distribution. So in this case, it's uniform. All of the different variables have the exact same frequency to them. Then you want to select your sample size. So in the middle chart here, there's a little dialog box. We can edit that to say maybe we want to take a sample size of 50 people. And then the buttons at the top tell you how many times you want to take the sample of that size. So if we select it once, here are all of the 50 people, and then the statistic coming from those 50 people is on the bottom plot. So the average coming from a sample size of 50 is this little green bar that's at the very bottom. Now if you want to see the animation, the sample size does have to be smaller, so let's say a sample size of 5, and we do that one time. You can literally see those 5 individuals being pulled from the population and then their collective average coming into that bottom plot. So if you want to play around that for a little bit, just trying different parameters and different samples and different sample sizes, feel free to do that. But we'll go ahead and get started with number 1 in the lab here. So I'll reset. Explore how the shape of the population and sample size affect the distribution of certain sample statistics. Part A says specify a distribution for the population. Note the values of the population mean and the population standard deviation. So I'm just going to stick with what I have chosen right here. This is a uniform distribution for the population. That was what I picked in the initial dialog box. It has a mean of 25, and it has a standard deviation of 14.4309. So that's just coming from this top chart where it says population. It gives me all of those parameters right up front. I'm going to specify a fixed sample size. That's the dialog box in the middle. I'm going to say 15. And then specify the number of random samples. Let's say I want to take 5 samples. So I click the 5 times button. So 5 samples of 15 people each. Sketch or copy and paste the sampling distribution of the sample means. Well, that is again this little distribution at the bottom with the green bars, right? Each one of the values in that distribution is a sample average that is coming from each one of these 5 individual samples of size 15. So we'll go ahead and copy and paste that real quick. The snipping tool is a handy thing to use. So from this sampling distribution of sample means, I can see that the average of averages, right? So each one of the values that are coming down into this last plot are themselves means. So if I'm taking an average of the sampling distribution, I'm taking an average of averages. So that value is about 24.5141. And the sampling standard deviation is about 2.7271. Okay. Number 2, we want to show the first part of the central limit theorem is true for any population distribution. So if we remember, part 1 says that it doesn't really matter what the distribution of the population looks like. It could be normal, it could be uniform, it could be skewed, as long as we are taking samples that are big enough. The sampling distribution of sample means should be approximately normal, where the mean is equal to the population mean, and the standard deviation is equal to the ratio of the population standard deviation divided by the square root of n. So we kind of want to test that using this applet just to see if the central limit theorem kind of holds water with a simulator like this. So part A wants us to run it for a uniform distribution, which is what we have, from our experiment in number 1. So let's go ahead and reset here. First running the simulation for a uniform population. So we're just going to make note here that the mean for a uniform population here is, again, 25. And I want to use a sample size of 30. So I'll adjust the 15 that I picked from number 1 to a sample size of 30. And that's also the threshold for part 1 of the central limit theorem. It has to be a sample size that is big enough, and the cutoff for that is 30 or more. So our sample size is 30, and we're going to run this 30 times. Now, I don't have a 30 times button, but I can just hit this 5 times until I see the number of samples down here show up as 30. So I essentially want to hit it 6 times. 30. There we go. Okay. Now, what is the mean of the sampling distribution of sample means? Well, the mean on this last plot here is about 25.3115. And looking at this graph, it does taper to the left and to the right, and the majority of the values are kind of grouped in the middle here. I would say, yeah, it is approximately symmetric. Okay, we'll reset here. In part B, we want to run the simulation for a population distribution of our own creation. Now, what this means is that I'm just going to kind of click and drag around in the top plot here, right? So if we click and drag, we can make any looking graph that we'd like, but whatever your picture ends up being, just make a quick note of what the mean is. So for me, it's 24.1676, and then run it again. So we're same sample size here of 30. We want to take 30 samples of that size. So 1, 2, 3, 4, 5, 6. So I've got 30 samples here. Each have a sample size of 30. Looking at the graph, and it's got a rough symmetric shape to it. Majority of the values are in the middle. It tapers to the left, it tapers to the right. So I'm going to check yes. And the mean is pretty close. It's 24.3927. So in part A and in part B, our mean of the sampling distribution of sample means is very close to the population mean. One more test here. We're going to run the simulation for a right-skewed population. So we're going to click Options and Edit to go back to the different types of distributions for the population. I'm going to click right-skewed, Compute. So there I've got a right-skewed graph. The mean there is 14.0519. So we've got a right-skewed distribution. Sample size, let me adjust that back to 30. And we're going to click this button 6 times. So I've got 30 samples, and it looks like the sampling distributions of sample means average mu sub x bar is 13.6722. And it is approximately symmetric, tapering left and right, got a majority of values in the middle. So part D, considering the results A through C, did the central limit theorem hold up? Explain. Well, yes, obviously it held up because every time we had mu, the population mean, approximately equal to mu sub x bar, the average of the sampling distribution. One thing we didn't check, but we could, would be to see if sigma sub x bar was approximately the population standard deviation divided by the square root of n. We could do that. And every time, because we were taking a sample large enough, we also had a sampling distribution that was approximately symmetric. So part 1 of the central limit theorem, according to this simulator, looks pretty good. So however you want to explain that in part D, I will leave that up to you. In number 3, we're exploring the second part of the central limit theorem, which says that if we already know that the population is bell-shaped, remember in this last one that we just did, we were changing, in number 2, we were changing the shape of the distribution every time. In part A, it was uniform. In part B, we kind of made up a shape. In part C, it was skewed. So part 1 was for all different types of populations. It was giving us basically a threshold on the number of people that had to be in our sample to make sure the sampling distribution was approximately normal. In the second part of the central limit theorem, we're already assuming that the population is bell-shaped. When that happens, according to the central limit theorem, the sampling distribution of sample means will be approximately normal for any sample size. So in this one, again, we're already specifying the shape of the population, and given any sample size, the sampling distribution will also be approximately normal. So we're going to test that now. Let's do options, edit, and excuse me, this time we're going to click bell-shaped and compute. So we're already specifying here that the population has a normal look to it. So in part A, what do you expect the mean and the standard deviation of the sampling distribution of sample means will be when the population is set to be bell-shaped with a mean of 25 and a standard deviation of 5? Well, if part 2 of the central limit theorem is correct, then mu sub x bar should be equal to mu, which is, that kind of looks like not equal to, let me fix that. Should be equal to mu, which is 25, and sigma sub x bar, the standard deviation of the sampling distribution, should be sigma divided by the square root of n, which in this case, sigma is 5, and the square root of n, we're taking samples of size 15. And I'm getting that from part B. I'm kind of looking ahead there. So if I'm doing 5 divided by the square root of 15, then our sampling distribution of sample means standard deviation should be what? Let's do that on the calculator here. Let's see. 5 divided by the square root of 15 should be approximately 1.291 for rounding to the third decimal place there. So let's go ahead and see what happens. So we're going to run this simulation. We're going to use a sample size of 15. So adjust that middle dialog box. And we want to do this 30 times. So I'm hitting the 5 times button 6 times until I get 30 samples of size 15. Let's see. Again, the population's mean was 25. We come up with a sampling distribution mean of 24.9809. Well, that's pretty darn close. It is approximately symmetric, and the sampling distribution standard deviation from the applet is 1.5178. We were looking for approximately 1.29, 1.51. It's not too far off, considering that this is, a simulation going on here. So this also shows us that even when the sample size is small, here it's definitely below 30, our sample size is 15. Even when the sample size is small, if we already know something about the population, we can again assume that the sampling distributions of sample means shape is going to be approximately normal, and we've got a lot of nice properties that go along with the normal curve. So really the whole point of this lab was just kind of proving to ourselves part 1 and part 2 of the central limit theorem. Whether we know something about the population or we know something about its shape and the size of sample that's being taken, we can make some really nice conclusions about the sampling distribution, especially if it is normal. Then we've got all of the properties of the standard normal curve at our disposal. So let me know if you have any questions about this lab, and I will leave those parts on the explanations for you to fill in, and hopefully this was helpful. We'll see you in the next video.